Hello, this is Mohammed Didia. This is Module 2 of an on-demand dynamic supplemental book on liquid formulation. This book makes learning faster and easier. In this particular portion, there are three submodules containing related videos. First is solute, solvent, and solubility. Second is on pH, co-solvent, and complexation. And the final is quality, specifically quality by design, stability, and chemical kinetics. This gives a comprehensive understanding of physicochemical characterization of solution formulation. In future modules, we would look at suspension and emulsions. Solubility and solubility product, KSP, are well known. The solubility product constant is an equilibrium constant of a solid, especially ionic solid dissolves. It dissolves into ionic form. For example, when sodium chloride dissolves, it dissolves as sodium ion and chloride ion. And at saturated solution, the solubility product is molar concentration of sodium and molar concentration of chloride in that solution. The saturated solution solubility product is 37.6. And KSP is high. It shows that sodium chloride is highly soluble. In this case, 36 grams per 100 ml in water. So this kind of knowledge is extremely important in calculating solubility of compounds and impact of common ion, such as if we were to add chloride ion into a saturated solution, sodium chloride will precipitate. For myself, we have looked at very complex KSP for hydroxyapatite, teeth mineral, and effect of strontium. And this is given by a very complex equation, and reader can look at the reference to it. Involves calcium, strontium, and phosphate. Different diffusions and concentration are involved in establishing solubility product. And it is 1 times 10 raised to minus 132 as determined by dissolution model, indicating teeth mineral is very insoluble. However, in the mouth, we have acid constantly present, so teeth mineral will dissolve at very slow rate. In this particular textbook, we will look at video simulation to understand what solubility is, rather than go into highly mathematical model. So polar solutes such as sodium chloride dissolves in water. What are the molecular interactions in that? And molecular interaction between polar solute and polar solvent forms solution. We know that from sodium chloride, sugar, and many, many molecules. This involves intermolecular forces between solute, case, for example, sodium chloride, and solvent, in this case, water. This intermolecular force between solute and solvent is much higher than intramolecular force. That is the force within sodium chloride that's holding that molecule. So if this intermolecular force is higher, then material will dissolve and form a solution. In this example, green here is sodium chloride, and red and white is water molecule. We'll see in the simulation how hydrogen bonds are formed. We'll see here how oxygen, electronegative element, attracts electropositive sodium, and then molecules of oxygen then surround it. Similarly, hydrogen attracts chloride, and the molecule of water then surround it. So you will see that simulation on how molecular interaction between polar solute and polar solvents take place. you start seeing the water molecule and attracting and carrying sodium ion. Similarly, chloride ion is attracted and is carried away. And this is the mechanism by which polar solvents dissolve polar solute. Non-polar solute and non-polar solvent dissolve with a called London dispersion force. And again, molecular interaction between non-polar solute and non-polar solvent or London dispersion forces of the solute must be broken down by the force of attraction between the solute and a solvent molecule. So there is a cohesive force and an adhesive. That's how non-polar solute and non-polar solvent dissolve. In this simulation, you will see that electron density shown here. Electron density changes in the molecule with D plus and D minus. D minus means more electrons are present in this part of the molecule and they get attracted by less number of electron positive portion of that molecule. In this simulation, you will see electrons moving and then London dispersion force, which attracts delta minus and delta plus. And you see pluses and minuses, and another molecule or another atom is attracting. And even though electrons will move, it will adjust accordingly. Next question then is immiscibility of non-polar molecules in a polar system. In this case, oil and water. It's well known that oil and water do not mix, they separate. In this example, pentane is represented as non-polar oil, which is insoluble in water, and it's shown as blue and green, and water is shown here as red and white. So attractive forces within this mixture are London dispersion forces, dipole-dipole, and hydrogen bond between water molecule and London dispersion forces within pentane. The hydrogen bond between water molecules are much stronger than London dispersion forces between water and pentane. Water will squeeze the pentane from the system. As we look at the simulation, you will see water molecules mobility and hydrogen bond squeezing out pentane from the mixture. This is a mixture of pentane and water, and it's hold static. And very shortly, you'll start seeing water molecule attracting each other by hydrogen bond formation in this mode. And as it starts attracting, the pentane is being squeezed out and it will separate. And the simulation shows within entire system will separate. Now you can see the separation of pentane or squeezing out because of the strong hydrogen bond formation between water molecule. So we now see how polar solvents dissolve polar molecule, how non-polar solvents dissolve non-polar, and how immiscibility works from a very practical. In order to solubilize solute, we need to have higher molecular interaction between solute and solvent as compared to the solute alone or solvent. So in practice, what generally we do is to add solute into solvents. Solvent here is a substance that dissolves, for example, water. Solute is the substance that's dissolving to form a homogeneous mixture at a molecular level. And solubility is upper limit of solute that can dissolve at given temperature and pressure. Because temperature and pressure both can affect solubility of solute in a given solvent. We can prepare supersaturated solution where solution contains more solute than it can dissolve into a solution phase. And we'll see in this simulation what you will experience in the laboratory. So we start adding solute. Initially, all the solute is able to dissolve because they are undersaturated and the concentration of solute is below the solubility at this. So you see it's dissolving and you see very clear solution. As we keep on adding more solute, it will not dissolve until maximum solubility is reached. And that's what we see, a solute sitting at the bottom or floating. So let's look at the example of nonpolar solute solubilization ethanol. Retinol is a known vitamin A. It's a fat soluble vitamin and is practically insoluble in water. If I were to add retinol into water, water will squeeze retinol out, as you saw in the previous video on pentane. Non-polar retinol solubilization ethanol. Ethanol has intermolecular forces, hydrogen bond, as well as London dispersion forces. Ethanol molecule is CH3, CH2OH. You will see much stronger hydrogen bond with ethanol alone. Retinol has very little hydrogen bonding, though there is an OH group. However, predominantly driven by London dispersion forces as shown here. And whenever we have a positive delta charge, less electron, it is balanced by a higher number of electrons on the other part of the molecule as shown. There would be an attraction between two different retinol molecules through London dispersion forces here, T minus attracting towards T plus. When we add ethanol, solubility of retinol increases to 50 milligram per milliliter. The mechanism of solubility is when we add ethanol to retinol, there is a London dispersion force between ethanol and retinol. And this London dispersion force breaks down retinol's internal or intramolecular London dispersion force. And that allows ethanol to dissolve retinol. And ethanol is very good solvent. It has both hydrogen bond capability and very good London dispersion force. So it's very commonly used solvent in pharmaceutical and cosmetic. Another feature is when we add multiple solute in a solution, we need to be aware of all these molecular interactions. Different solute in the same solution can affect each other's solute. For example, if we add preservative, which is soluble in water, and we add sodium chloride, which is soluble in water, sodium chloride solubility will affect the preservative solubility in the same solution. So in physicochemical interaction, we need to consider entire formulation, not just single substance. The well-known proteins, which is called salting out and salting in. At low concentration of sodium chloride, protein dissolve with higher solubility. As we add more sodium chloride, solubility of protein declines and it precipitates. And this is all due to hydrogen bonding or ionic bonding of sodium chloride with water and ionic bonding of sodium with protein at low concentration. Small amount of salt. That will increase solubility. If we add more salt, it will start precipitating protein. And this is simply related to the negative charge on the protein, which is sodium chloride. So solubility of protein will increase and then it will start decreasing as more salt is added. This is due to hydrogen bond, water pulling sodium chloride out of protein at this stage. Whereas in this particular portion, sodium ion is attracted towards protein. Sodium ion is attracted towards protein. As proteins have both pluses and minus charges, proteins are made of amino acids, and this negative charge, it will attract sodium ion and dissolve more. But as we add more and more sodium chloride, water will start pulling sodium ions out and it will precipitate.